Well, good morning, everybody. This is Mathman, and we're at a point where I think maybe a little bit of mathematical history might be appropriate now that we're knee deep into calculus. We've already covered differential calculus, and we are beginning to move into integral calculus. We've taken a look at the fundamental theorem of calculus, as it was devised by Riemann. It's interesting to note that neither Isaac Newton nor Gottfried Leibniz were able to put calculus on a theoretical or theoretically accepted mathematical foundation. It wasn't until excuse me, it wasn't until the middle 1860s when Bernhard Riemann was able to put the connection between his Riemann sum his limit of a sum that used geometric, accepted, known, proven geometric methods to find the area of an object. In this case, it was a geometric method to find the exact area under a curve between two points on the x-axis, and he equated that and showed that it was equivalent to the definite integral of the function between those 2 points on the x-axis using differentials, the concept of differentials. So that gave calculus a firm foundation, a theoretical foundation. Up until that point in time, there wasn't much of a distinction between the sciences as there is today. I mean, today we have biologists, we have chemists, we have astrophysicists, and we have cosmologists, and all different forms of sciences that have been broken out into their own disciplines. Back in Isaac Newton's day, or Gottfried Leibniz, even up until the middle 1800s, scientists were called natural philosophers. And that's why when you get an advanced degree in physics, it's a PhD in physics. That's a doctorate of philosophy. Medicine, you get an MD, medical doctor, but there's no physical doctor, there's no chemical doctor. These different sciences are all basically branched out from the concept of a natural philosopher, which was somebody who studied nature. In fact, many of the early scientists were polymaths. They branched out into many different areas outside of a particular science. You know, today you wouldn't see a chemist making a proposal on astrophysics or cosmology, but back in Newton's time, there was no defined areas of discipline, of branches that one was an expert in. They followed multiple paths, or whatever interested them. In fact, Isaac Newton was even famous for his interest in alchemy, which is more of superstitious magic, Merlin sort of thing, than it is any kind of a science. It's certainly not chemistry. But back in the mid 1600s, Isaac Newton was a student at Cambridge University back in the 1660s. And in 1665, they had to close Cambridge. He was studying mathematics, science. I guess he was I think really headed for the ministry. He really had a very strong interest in religion. In fact, he wrote more on religious topics than science by far. Many of those writings have been lost. Only the important writings such as optics and Principia remain because they changed the world. But Isaac Newton was a young man, and 1665, and he was sent home. They closed Cambridge University, and he went home. And he had a very dynamic mind, and he was contemplating the laws of physics, and he was contemplating gravity. And he came to the conclusion that the force that caused things that you drop out of your hand to fall to the ground was the very same force that kept the moon in orbit about the Earth, and the same with the Earth about the sun. That it's this gravitational force, and he thought of it in terms of every piece of mass that comprised the Earth as each contributing to this attractive force, and he needed a mathematics to help him show that the concentration of all of the Earth's mass at its center of gravity, or central point, was equivalent, and that the effect of the Earth's gravity on the moon and vice versa, the moon's gravity on the Earth, was dependent upon the distance between the centers of the two objects, the line distance between the centers. He called that R, and it was inversely proportional to R, or that distance, or by the square of that distance, actually, R squared, and directly proportional to the masses of the two objects multiplied by the gravitational constant. And so he needed to develop the mathematics to be able to develop his ideas further, and to show that this idea would yield to our observations that the planets were traveling in elliptical orbits around the sun. So he was thinking about these things, and Newton was the kind of guy that wasn't very interested in publishing information on his own, but he was kind of like Carl Gauss, Carl Augustus Gauss, who's the greatest mathematician. They're probably 50 years ahead of his time in mathematics, so the greatest mathematician who ever lived. And he wasn't interested in publishing. He just put these notes together. He had a little, like a diary, and put these notes together, and it wasn't until he passed away that people realized that there was some earth-shattering revolutionary mathematical insight into some of these notes that Gauss had. But he wasn't interested. He was a very humble man. And the same went with Newton. He was more interested in solving the problem to his own satisfaction than he was necessarily in publishing. And he had developed the idea, although he was thinking in terms of this concept called fluxions, which are the same things as infinitesimals of differential calculus. And he published these ideas about 20 years after he first conceived of them. So Leibniz, who apparently, now this is the interesting thing, mathematicians, they take Leibniz aside, but Newton was kind of an odd character, and he didn't, the notes were all over his house. He was constantly thinking about problems all the time. He was never really concentrating on, he wasn't very social, for one thing. He was almost a recluse. He did have a friend in Sir Edmund Halley, and Halley realized that the work that Newton was doing was not only revolutionary, it was absolutely necessary to advance science. And so he stole Newton's papers to have them published. I mean, Newton wouldn't have done it. Newton didn't do it, but except for Halley. But there was some major controversy between Newton and the mathematician Gottfried Leibniz. And Leibniz was some kind of an German ambassador to England. At the time Newton became a member or even headed the Royal Society. Now, the Royal Society was the elite scientists of their day in England, and today it's still a highly respected institute, scientific institute. It's like the Academy of Sciences in the United States. If you're a member of that, you've really been an accomplished scientist. So Leibniz, being a mathematician, being again one of these generalists, natural philosophers, had contact with Newton during those days, and he certainly saw some of Newton's earlier publications, which mentioned and used fluxions in mathematics, the calculus, as an aside, or published as an appendix to his works. And they supporters of Newton, his members of the Royal Society that backed Newton, suspected that Leibniz had plagiarized the work of Newton. Now, reading about Leibniz himself, he was no great guy himself. I mean, there's plenty about him that's suspect. I mean, he was known to have backdated letters, backdated information, which today would be, really scandalous. Back in those days, plagiarism wasn't accepted, but it wasn't highly condemned either. So this controversy raged through their lifetimes, from the later 1600s into all the way until Leibniz died, which was around 1711, and I think Newton died in around 1727. He lived to a pretty old age. I think he was in his 80s. Newton was one of those very rare geniuses. I mean, everybody puts their attention to Einstein and his, and I'm not trying to take away anything from Einstein because he revolutionized the way we think about the universe. But Newton was a very special kind of individual. Now there is a an interesting anecdote that I read once that Carl Sagan had written about Newton. And the Bernoulli brothers, they were very early, they were mathematicians in the 18th century. Two brothers, Johann and Jacob Bernoulli, they took calculus and advanced it early on. And I forget which one. I think it might have been Jacob, or it was one of the two. I don't know if they mentioned the brachistochrome problem. No, I don't think I have anything about the brachistochrome problem. This problem was published and by one of the movies. I don't know if I have that here. And it was sent out, and this was a common problem, a common practice back in the from the 1500s on. Mathematicians would send out problems and disseminate them all over Europe to the top mathematicians of the day in their era, and they would be asked to solve the problem within a given period of time. And I think the brachistochrome problem was given a year. I'll draw it on my sketch pad just to give you an idea of what the problem entailed. But Isaac Newton was about 54 years old by this time, and usually flashes of genius occur very early in a person's life. Usually they'll have some phenomenal flash of insight into something that changes the world, and then for the rest of their life they don't contribute much of anything. Well, Newton wasn't like that, and there was a rift between continental Europeans and England in the 18th century, especially over the controversy over who first devised or came up with calculus. I mean, Newton accused Leibniz of stealing it from him, and so there was bad blood that went around, and Europeans didn't generally like involving or corresponding with the Brits, and I think the feeling was mutual. Eventually, historians and mathematicians, they settled on that they both independently came up with the calculus from two different independent paths. There's some lines of evidence that support both, but interestingly, there's some evidence too that it's possible that Leibniz did plagiarize. But anyway, I'm not going to go into that kind of detail. But Newton was about 54. Now, this problem had been in circulation throughout Europe for about a year, and it was the day before the deadline that the Bernoulli had given to solve this problem. And it was the day before that deadline that Newton first received the problem. And overnight, he solved it anonymously, sent it back to Bernoulli, and Bernoulli knew who it was. He said, "I know the lion by its claw." Everybody knew that Newton solved the problem. But in so doing, Newton invented an entirely brand new branch of mathematics called the calculus of the variations. At 54 years old, he invents a whole new branch of mathematics. So that tells you something about the mind of this man. It's just phenomenal. It's beyond comprehension when it comes to his genius in mathematics. Also shows that an individual should never give up. That you're never too old to be to contribute to science or any other arts in any way, because well, I think in the arts people recognize musicians. Often it's in their later years that they really get attention. The same with artists, but that kind of recognition doesn't happen often with scientists. They rest on their laurels. They're recognized for their contribution, but their contribution was a flash in their youth, and a star burnt out, and they get recognized through their lives for it, but they're not given, let's say, any credit or thought of as, well, they're past their prime. They no longer can contribute. And Newton showed that this wasn't so. One last story, and this is a sad one. It's found in this 5 equations that changed the world. Again, it goes back to the Bernoulli brothers. This was Johann Bernoulli. Daniel was the son of Johann Bernoulli, and Johann didn't want his son to become a mathematician. I don't know. Maybe it had something to do with the competition. I don't know. The Bernoulli brothers were very competitive, and they weren't very nice. It seems that a lot of these guys are either eccentric or not very nice people. And in spite of his father's denial of him to follow mathematics, he wanted Daniel to be a medical doctor, and which at the time wasn't really, it was more superstition than it was a science in the 18th century. They didn't even have a theory of germs at that time. But Bernoulli didn't follow his father's, Daniel Bernoulli didn't follow his father's wishes, and there was some bad blood between the two. And Daniel Bernoulli came up with the hydrodynamic equations, which are so tremendously important. I mean, they've revolutionized our lives. I mean, the basic principles underlying flight, aircraft, lift, pressure differentials, all comes out of Daniel Bernoulli's hydrodynamics. Well, before Daniel was able to publish any work on his hydrodynamics, differential equations, his father stole the work and published it under his name. He hadn't been very productive up to that point, and he really needed something to stay in the limelight from in the scientific world and mathematical world, and so he stole his son's work. And for some years, Johann was recognized as the I mean, this is awful. I mean, that a father could do that to his own son. It was, Daniel had a good friend in Leonard Euler. They were contemporaries. They I believe Euler went to Petersburg, which was the Russian center for arts and sciences and learned. They had a university there. It was a brand new university. They were trying to get good people and professors. They were competing with the rest of Europe. And so I think they made an offer to Euler, and Euler brought Bernoulli along, Daniel Bernoulli. They were good friends. And eventually, I think it was through Euler's influence, because Euler was a renowned mathematician, that people began to realize that it was Daniel Bernoulli who was the true author of the hydrodynamics equations, and he finally got his due, and his father acknowledged begrudgingly that he indeed wasn't, that he plagiarized, that he had stolen his son's work and then published it under his name. So this is a dog-eat-dog world. I mean, there's nasty stuff that goes on. I mean, there is a very definite human element in the world of science and mathematics, and it's a shame, but it's there. We're all human. But I thought a little bit of history would be appropriate at this point, because so many students don't realize. They just think of these guys as walking around, and in the their mind is somewhere so high and above, and that there's nobody that could ever conceive of coming up to their status. I mean, Leibniz, when he first published on calculus, his first publication of calculus was so convoluted and difficult to understand. He didn't try to make it clear for anybody to really grasp, because he wanted to be perceived as being high and mighty and superior, intellectually superior to anybody, and only he could understand this stuff. And unfortunately, there are people like that on ego trips. But even though I don't do a tremendously good job of it, I at least try to do my best to take these concepts and make them as easy to understand as I can in conveying this information. I just love mathematics, and I love the beauty of it. I think it's the foundation of our universe. I think our world universe is inherently mathematical. I don't think we invent math. I think we discover it, and I think there's a critical difference between the two, because discovery suggests that this is something inherent, something integral to the universe itself, and it's insightful about the universe. It's the body, the structure, the way it is the substance of the universe, whereas the other is more descriptive, and the universe is what it is, and we've layered on mathematics post hoc to give a description to how the universe works. See, there's a difference in the philosophy and the way of thinking. One last story, I think, which is important. Math students struggle over calculus. I think, unfortunately, too many students find calculus way too hard to understand. And I blame mathematicians for that, because they layer on 300 years of theoretical development onto the subject that I mean, Newton did not think that first, what do I need? What are the conditions I need to do this? Does the function have to be continuous on the interval in which, all of that stuff? The theoretical aspect of it, uh, and the theoretical descriptions of calculus weren't really thought of by Newton. In fact, he took derivatives by looking at tables and deriving differentials by in tabular form, and that's the way many mathematicians did things until there was a theoretical basis. And again, as I mentioned earlier, mathematics didn't have a theoretical basis for calculus until Riemann, some 150 or more years after calculus first was developed by Newton and Leibniz. Well, back in Newton's day, and maybe a little later, it was a Bishop Berkeley. He was a Catholic bishop, and his main criticism, he was a philosopher, and his main criticism about the calculus was the idea that you had these things that were smaller than any number but greater than zero. And it's what these infinitesimals were. They were in essence, they had properties that were both zero and mathematically real. I mean, you can't sum up zero areas and then come up with an area. So there was some dynamic physical aspect of it that was real. Otherwise, you wouldn't be able to sum these things up. But at the same time, they were infinitesimally small. So they were in essence zero. And this was conceptually very difficult for people to accept. And this Bishop Berkeley called infinitesimals in differential calculus the ghosts of numbers recently departed. And that was a valid criticism until Riemann showed that there was a way of thinking using limits that equated the infinitesimal concept to algebra, and that's really the beauty of, or not algebra, but geometry and algebra. That's the beauty of the fundamental theorem of calculus, is to show this equivalency. But the actual concept of an infinitesimal and differential calculus wasn't demonstrated to be true until 1966. Now, I was about 11 years old in 1966. It took over 300 years before the way Leibniz thought, the way Newton thought about calculus and these infinitesimals was actually shown to be valid, that there was credibility to the concept. And so students shouldn't think that this, why am I here? Or this is too difficult. Because it took the mathematicians themselves, and they don't tell you this when you're in college, in school. It took them 300 years to put calculus on a theoretical basis that was sound. So I think, if somebody is interested in teaching students, they try to make it different. They try to make it simple to understand. Whereas somebody who is got to show that they are intellectually so much higher than somebody else, they won't do what they can to help a student. So that I find shameful, because this is such a beautiful subject. I think it's every bit as beautiful. It is how the universe is, and so we need to try and bring out that aspect about mathematics and how beautiful it is. And I think one person who really went out of the way and did a good job of it, at least for most people, because most people aren't going to know as much about calculus, but Theone Pappas was a school teacher in California who wrote some years back, I think these are 20 years old. I don't know if she's still alive. These were first copyrighted in 1986. This book, A Joy of Mathematics, and it goes. These are vignettes. It's not a text, but these are vignettes that are no more than 4 or 5 pages that talk about all the different areas of mathematics that are beautiful and so fascinating, and it's just a tremendous read for anybody, because all you have to do is add Mobius strips, topology, all of this. She makes it very simple. Pascal's triangle and Fibonacci numbers, and we'll be getting to Fibonacci numbers once we're done with calculus, differential equations. She wrote a sequel book called More Joy of Mathematics, and she's written, I don't know, 10 or 11 different publications. They're all the same. They have 4, 5, 6-page vignettes that thoroughly cover mathematical topics. Here's tessellations. My aunt was published in tessellations. She was quite renowned as one of the, these are Penrose tiles. She was quite renowned as an amateur mathematician. She's listed in Wikipedia for her proofs. So these are things that I just wanted to convey to those who are watching these videos, and I'm hoping that they can be helpful to people who are studying the subject, because too many times I hear friends, asking me to help their kid on a problem, or and I just think it's such a shame that the colleges can't do this on their own. And so I try. That's why I put these together. I don't think mathematics is really is a viral video subject, obviously. But I do get joy in talking about these things. I wish there would be more that would take interest, but who knows? Maybe one of my videos can be helpful to somebody, and that's the object behind me making these things, and hoping that people will come to an appreciation of mathematics for the beauty it is. It's actually intellectual beauty. So anyway, with that, this is Mathman wishing you all best, and we'll get back in our next video to different methods of integration and their applications. So I wish you all the best. This is still the COVID season. Stay safe, wash your hands, social distance, and wear masks.